Hi everyone, welcome to today's lesson on types of reaction. In this lesson, we're going to learn about the different types of reaction, how to classify the different types of reaction, and then predict products based on the different types of reactions. So the first type of reaction we're going to look at is a synthesis reaction. So a synthesis reaction involves the combination of two or more substances to form a compound. And so usually it is two reactants forming one product. The reactants are usually elements, and the general formula for a synthesis is A plus B forming an ionic compound AB. Okay, so keep in mind that this compound here, this is an ionic compound, meaning that when we're forming this ionic compound, we do need to use the ionic compound rules. So let's take a look at a few examples here. I have two iron metal reacting with oxygen gas to form iron 2 oxide. So once again, if you take a look at FeO2, we have the Fe2 charge with the oxygen with a 2 minus charge, and then they cross over, reduce to form iron 2 oxide. In the second example, I have sodium metal combining with chlorine gas, and that forms sodium chloride. To get the sodium chloride ionic compound, I'm looking at sodium with a charge of 1 and then chlorine with a charge of -1. And once again, when they cross over and you simplify, then this becomes NaCl. So just a reminder that when we're forming ionic compounds, we do have to use the ionic compound rules. So that is the first type of reaction that we're going to take a look at. The second type of reaction is a decomposition reaction. So a decomposition reaction involves the breaking down of a molecule into simpler substances. And so usually there's only one reactant, but we get two products. So the general formula is AB, this ionic compound, decomposing into its elements, A and B. So a few example, we have tin 2 oxide, that decomposes into tin metal and then oxygen gas. And then we have NaCl, that decomposes into sodium metal and chlorine gas. Just a reminder here that oxygen and chlorine gas, these two are diatomics, meaning that when they are on their own, they're going to exist as a pair. So once again, just a reminder, we have 7 diatomic elements. We have iodine, or I, bromine for brot, chlorine, clay, fluorine for oxygen, or R, and then nitrogen for new, hydrogen for home. So I brought clay for our new home. Once again, that's an easy way to remember the 7 diatomic elements. The next type of reaction is a single replacement reaction, and this involves replacing one atom in a compound by another atom. And so the reactants are usually one element and one compound, so that's kind of its unique identity. And just a note that the cations replace the cations, the anions replace the anions. So let's take a look at the general formula. I have element A combining with a compound, so BC, and one of those are going to get replaced to form a new compound and a new element. So if I take a look at this example here, A is going to go in and replace cation B, and so that's why this is called a single replacement, because an element is replacing a single element of a compound. So if I take a look at the examples, I have potassium metal. Potassium metal is going to go in and kick out or replace the aluminum atoms. And so I have potassium chloride as the new compound, and then aluminum metal, that's the element that got kicked out. Okay, chlorine gas. Now chlorine gas, this is a nonmetal. This is usually an anion. And so anions replace anions. So chlorine is going to go in and replace bromine. Bromine is going to get kicked out. And so the new compound is going to be with sodium chloride, and then bromine gas, that's going to be the element on its own. Okay. Once again, with all these chemical reactions, the order doesn't matter. So I could have a compound Okay, I can have a compound first, followed by an element, but the process is the same. This metal here is a cation, and it's going to go in and kick out the copper. So I form my new compound, which is iron 2 chloride, and then the copper atoms that got kicked out, that is on its own. So that's single replacement. Double replacement, like its name suggests, we're going to be exchanging not just one, but kind of a group. Okay, so double replacement involves an exchange of atoms or groups, and the key thing here, it's between two different compounds. And so the way to identify double replacement reactions is when you have two compounds as your reactants. And a lot of times when we learn this in junior science, we use the term trading partners, trading dance partners. And the idea is that the cations will replace the cations, the anions replaces the anions. And so the general formula for a double replacement reaction, we have AB plus CD. And let's take a look what happens. A here is going to swap partners with C. So we have A with D now, and then C with B. Okay, so just a reminder that cations replace cations, anions replace the anions. So let's take a look. My first compound here, in my first example, I have sodium sulfide. That is reacting with another compound, aluminum fluoride. And so this is a double replacement reaction because in my reactants, I have two compounds. So the two cations are going to replace each other, the sodium with the aluminum. Okay, so when you're forming your new compounds, we're forming our new ionic compounds, we use the ionic compound rules, right? So I have now sodium, which is a charge of 1, combining with fluorine, also a charge of 1 or minus 1. And so when they swap, we get NaF. Okay, so that's this NaF here. We have aluminum, charge of 3, combining with sulfur, charge of 2 minus. Okay, and so when we cross that, we get Al2S3, and that's the other compound. Okay, and then we balance our chemical reaction. Another example here, I have H3PO4 or phosphoric acid reacting with iron 2 nitrate. Once again, how I identify that this is a double replacement is when I look at it, I see that I have two chemical compounds. So anytime you have two chemical compounds, this is a double replacement reaction. The cation, in this case, this is the H+, is going to replace the other cation, which is iron. So we now have H combining with my nitrate ions. So I get HNO3, which is this compound here. And then now I have iron combining with phosphate. So I cross that, reduce, and I get Fe, well, in this case, this is Fe2+. So I get Fe3PO4 2, which is the other compound, and then I can balance my chemical reaction. There's another type of chemical reaction called a neutralization. Now, a neutralization is actually a really special case of double replacement. A double replacement, remember, it's when you have two compounds reacting together. Neutralization is when one of the compound is an acid and the other compound is a base. So when I have an acid compound and a base compound, when they react together, they're always going to form water and salt. And so salt is really just any other ionic compounds that's not an acid or base. And just a reminder, an acid is an ionic compound that starts with H+, and a base is an ionic compound that has the cation OH- or the hydroxide anion. And so salt is therefore any other ionic compounds. So anytime when you look at a compound, if it starts with an H, the hydride ion, that's an acid. And if you look at a compound and ends with an hydroxide anion, then that is going to be a base. General formula, once again, acid plus base, giving us a salt and water. So a few examples here. I have hydrochloric acid, HCl, reacting with NaOH. Now we treat these the same way. The cation is going to replace the cation, and in that way we get NaCl, the salt, and water. Okay, so we will always get water in some form of salt. Next example here, I have sulfuric acid reacting with lithium hydroxide. Same idea here. When I look at it, this is an acid because it has an H. This is a base because it ends with an OH. The cations are going to replace each other. So now I have lithium sulfate and then water. Once again, we always have water. And so this is a neutralization reaction. It's just a special case of double replacement, but we can treat it the same thing as a double replacement. Cations replace cations, anions replace anions. And kind of this sixth type of chemical reaction here is a combustion. And a combustion is a rapid reaction of a substance with oxygen, and it produces a huge amount of heat, and usually we get a flame with that as well. And so a lot of times when we're burning something, a candle, or we're burning our firewood, anytime we're kind of burning something, that is usually a combustion reaction. And so the general formula for a combustion reaction, we need to have a hydrocarbon, and it needs to react with oxygen, just like a fire. If there's no oxygen, then nothing can burn. And so a hydrocarbon is usually anything that has carbon and hydrogens in some sort of amount. So here I have CXHY. So X can be a number, Y can be a different number. So for example, CH4, this is methane. We can have, for example, C2H6. This is ethane. And so any kind of combination with carbon, hydrogen, sometimes we'll have oxygen in there. That is called a hydrocarbon. And so you need a hydrocarbon in order for you to have a combustion reaction. And for a combustion reaction, the products are always going to be carbon dioxide and water. Okay, so it's always going to end up with some carbon dioxide and water. We can take a look at this example. I have C5H12. So again, when I look at it, I have some combination of carbon and hydrogens. So this is a hydrocarbon. We have oxygen, and it will always produce carbon dioxide and water. Okay, so let's take a look at a few of these examples here. We're going to classify the following reactions, predict the products, and then balance the reactions. So the trick here is to just look at the reactants, because just by looking at the reactants, that is enough for us to predict the products. Okay, so we're going to look at reactants. So let's take a look. So in the first reaction here, we have calcium and oxygen gas. So if we're looking at it, we only have two elements here. We have calcium metal and we have oxygen gas. So the fact that this only has two elements, that means this reaction is actually a synthesis reaction. Remember that for a synthesis reaction, we have A plus B giving us the compound AB. So let's see. We have, this is A, the calcium, and this is B, this is the oxygen. Just a reminder that when we're combining, we have to look at the charges again. We cross them, reduce them, and we get calcium oxide. So I have calcium plus oxygen gas give me calcium oxide. And then finally, to balance it, I'm going to put a 2 in front of calcium and then a 2 in front of calcium oxide. Example B here, I have magnesium plus hydrobromic acid. So magnesium here is an element, hydrobromic acid, this is a compound. So when I have a single element with a compound, what I have is single replacement. So let's take a look. Magnesium, this is a metal, it's usually a cation. Remember that cation replaces cations. So once I have magnesium ink replacing the hydrogen ion, then I get magnesium bromide. Remember, magnesium has a charge of 2, bromine has a charge of 1. When we cross it, we get MgBr2 plus hydrogen gas, H2. Now, hydrogen is a diatomic element, so that's H2. And then to balance it, then I'm going to put a 2 in front here, and now the reaction is balanced. Example C, I have barium nitrate reacting with sodium hydroxide. So it looks like I have a compound here and I have another compound here. And so when I have two compounds reacting with each other, this is going to be a double replacement reaction. Okay, so Ba is going to swap with Na. So I now have Ba, charge of 2, okay, OH, charge of 1, so BaOH2 plus, and then I have NaNO3. Okay, and then to balance it, I'm going to put a 2 in front of here and a 2 in front of there. Example D, I have aluminum. This is a single element reacting with copper 2 sulfate. This is a compound. Once again, if I have an element with a compound, this is going to be single replacement. Aluminum kicks out the copper, so I now have aluminum Al2SO4, and then my copper elements. To balance it, I'm going to put a 2 in front. Aluminum is balanced. I have 3 sulfates, and then 3 in front of C to balance it out. So let's take a look at example E. Now in example E, I only have one compound, NaCl. So when I only have one compound as my reactant, this is a decomposition reaction. And if you remember, for a decomposition reaction, I have my ionic compound AB, and it's going to split up or decompose into its individual elements. So NaCl is going to decompose into my sodium metal and my chlorine gas. And once again, because chlorine is a diatomic element, we write it as Cl2. Okay, and then all we have to do is balance the reaction. Example F. So example F, when I look at it, I have oxygen gas, okay? And then I also have my hydrocarbon. Remember, for my hydrocarbon, I have certain amounts of carbon and hydrogen. In this case, I have C8 or 8 carbons and then H18 or 18 hydrogens. So this is going to be a combustion reaction. And so for all combustion reactions, you're always going to end up with carbon dioxide and H2O. So when you're predicting your products, you can just write down carbon dioxide and H2O. And then for combustion reactions, it's a little bit tricky when it comes to balancing the chemical reactions. So I would say definitely practice balancing combustions. So this is going to be 2. So I have 16. That means I have 18 times 2, 36. And this is going to be 25. And finally, in example G, when we take a look at it, I have a compound here, HBr, hydrobromic acid, and then I have another compound here, magnesium hydroxide. Now, what's unique about this example is when I take a look at my compounds, I have an HBr. Remember, any ionic compound that starts with an H is an acid, and any ionic compound that ends in an OH is going to be a base. So this is my acid plus base reaction. In other words, this is going to be my neutralization. Okay, one of the products is going to be H2O, the other is going to be salt. But because this is a type of double replacement, then we treat this the same way as double replacements where we swap the cations. So I'm going to have Mg, charge of 2, Br, charge of 1, crossover. So I get MgBr2, and I get water. So I get my salt, and I get my water. And lastly, we're just going to balance it. So 2 in front, and 2 in front of the H2O. Okay, So there's actually another two types of reactions that I want to talk about. And the first one here is an endothermic reaction. Now, endothermic reactions, these reactions absorb heat from its surroundings. In other words, the heat enters the reactants. Okay, so that energy is absorbed and it's used to break down chemical bonds. And so if we touch an endothermic reaction, oftentimes we will feel a coldness or a lack of heat. And that's because the heat in our hands are the surroundings, heat from our hands is entering that system or that reaction. Okay, now this is a topic that we'll revisit later on, but I just want to introduce these two reactions, endothermic and exothermic reaction. So if you take a look at example 2 here, it says draw the energy diagram for the following reaction, then label H reactant, H product, and the change or delta H. Okay, so H here, you can think about this as the energy. Okay, so H reactant is the energy of the reaction. Now, technically, the correct term for H is something called enthalpy. And once again, this is a topic we'll revisit later on. So this H reactant represents the energy or enthalpy of the reactants. H product is the energy or enthalpy of the products, and delta H is what is the change in energy. So if we take a look at this example, we have hydrochloric acid plus energy. Okay, so that means this energy is being absorbed. If I put energy into HCl, I'm able to then decompose it to kind of H and Cl. Okay, now this is very rudimentary reactions here. It's not balanced. I didn't even count for the diatomic elements. Okay, but I just wanted to use this example just to show what endothermic and exothermic reactions are. Okay, so once again, this is very rudimentary. Yes, these are diatomics. There should be twos and this should be balanced. Okay, but I'm just going to ignore that for now. Now, when I look at this reaction, let's say on my y-axis, I have the energy. So this is just the amount of energy in a system in my molecules. And this can be kind of the time or the progress of the chemical reaction. So if I have HCl, I can arbitrarily set HCl to have a certain amount of energy. So let's say HCl, you have a certain amount of energy. So H reactant. If I input energy into this reaction, or if HCl absorbs energy, the energy level is going to increase to a certain point where that energy then splits up HCl into its constituents. So I have H and I have Cl. Okay, so this level up here, this is the energy of my products. That's how much energy my products have. And this difference here, from the reactant to the product, this is the change in energy. And so endothermic, these are reactions where energy is absorbed by the system, by the reactants, in order for chemistry to happen. Okay, so we tend to say that delta H is positive, meaning energy is absorbed. The opposite of endothermic reactions are exothermic reactions. And exothermic reactions, these reactions give off heat. Okay, so heat is given out to the surrounding, or heat exits from the reactants. Energy is released most of the time when we form these chemical bonds. So for endothermic reactions, when we're trying to break bonds, we need to input energy. Whereas for exothermic reactions, when bonds are broken, when bonds are formed, you release a lot of energy. And so if you touch an exothermic reaction, or if you're near an exothermic reaction, you'll feel the heat, and that's because the heat is leaving the reaction and entering its surroundings. And so a lot of kind of explosions or burning, these are all exothermic reactions, because if we're near the reaction, we feel the heat, and that heat is being given off when chemical bonds are being formed. And so like the endothermic reaction, we can draw an energy diagram to kind of show how exothermic reaction works. So we have energy on the y-axis again, time on the x-axis again. And once again, I can arbitrarily set kind of my H and my Cl, my reactants, to have a certain amount of energy. This is the energy of my reactants, or the enthalpy of my reactants. Okay. And if they come together, they form bonds, energy is going to get given off, so there's a decrease in energy in the system. And at the end, I have my products here, HCl, and it has a lower energy than that of the reactants. So the H product, or the enthalpy of the products, is a lot lower. And this change here, this change in energy, this is going to be negative because energy is being released. As always, please make sure you try the fun sheets and then check your answers with the fun sheets, and then email me if there are any errors or if you have any questions. See you all next time.